I will be defending my thesis today. And as you said, the title of my thesis is Autonomous Real-Time Model Updating within Digital Twin Frameworks for Thermal Systems. The publications that comprise my thesis is a peer-reviewed paper I published last August, and it was sent to IDETC. The other paper is still in that comprises my thesis is still in the submission process, but that will be sent to the journal Mechanical Systems for Signal Processing. Introduction. As naval systems become increasingly more complex, the need for data-driven solutions will become essential in order to maintain the health of the ship systems and subsystems. Over a physical systems life cycle, it will begin to change. This will happen either by degradation or operator actions. So its virtual model will cease to be an accurate representation of that system at its current state. But digital twins are a solution to this problem, as they can use sensor data to update model parameters in real time. This way by linking virtual and physical spaces together. The objectives of my work and what I'm trying to present and demonstrate today is I will provide a generic model updating scheme that can periodically update simulating models of thermal systems using real-time sensor data. Then I will use this model updating scheme I will test the robustness of this model updating scheme on two separate systems. So what is and why use a digital? The term digital twin was originally coined in the early 2000s. However, at that time, the hardware and software limited how far the research can go. But as technology has advanced and now it's more readily available to everyone, there's a renewed interest into the subject. So what is a digital twin? A digital twin, in short, is a collection of digital models that faithfully represent its physical system. When people talk about digital twins, they often refer to the physical system as a physical twin. This physical twin can be anything, any type of engineering system that could be virtually modeled. That being, it could be electrical, thermal, mechanical, etc. There are two key components to think about when designing and making a digital twin. So the first element is the modeling and simulations that create a virtual representation of the physical system. And then the second key element of a digital twin is the interaction or the feedback loop between that virtual representation and that physical twin. And now what use is a digital twin? Digital twins can be leveraged to optimize real-world systems and test new procedures, conduct virtual tests without the need of a physical system. One other major benefit is that, as I pointed out earlier, is that it can update models. But when constructing a digital twin framework, an important question arises: how will we update that virtual model? And that's what my research is focused around. Here's a quick overview of what a digital twin framework would look like. So as a operator makes inputs or changes to the system, that physical system or physical counterpart reacts and changes. And those reactions are captured by sensors instrumented throughout the physical counterpart. This sensor data is then relayed to the digital twin. Within the digital twin, you have a model updater in the virtual representation. The model updater goes through many permutations of model parameters, trying to minimize the error between the simulation data and the experimental data. thereby calibrating the digital twin to its physical twin. And once it's deemed calibrated, a projected digital twin response can be returned to the user. So going into our first system, the first system was a very, very simple small cooling loop. The cooling loop is composed of 5 main components. First, you have the pump, then you have the coolant plate with a heating pad, a flow control valve, a fan radiator, and an expansion tank. Water is pumped through the system by a centrifugal pump. The flow rate from this pump is captured by a flow rate sensor. Then it goes through a flow control valve. During the testing and results and discussion part, this flow control valve will be manipulated in order to simulate a blockage in the system. The water then flows through a coolant plate with the heating pad. The heating pad delivers heat to it, which is supposed to simulate various power electronics. This heated water is then captured by a thermocouple directly after it. The water then goes through a fan radiator, and this chilled water goes back out and is again recorded by another thermocouple. And then the water finally goes to its last component, the expansion tank. The purpose of this is just to regulate pressure and act as a reservoir. So now that I've introduced our physical twin or system, how does the data get from the physical twin to the digital twin? So the digital twin that's composed of the PSO updater and the virtual representation is on an x64 Windows computer, and the data is relayed to it via an IDAC with a thermocouple module. Other electrical components part of this is the power supply. The power supply does not have any direct communication to the digital twin. It's only responsible for providing heat to the coolant plate and controlling the radiator. Here is my virtual representation of that system. So in order to ground our physical system to our virtual representation, we need to tie it in with an input from it. So I chose to take the coolant temperature plate from the system and input it directly in the model. And then once I inputted it into the model, I then run it, and then I get the outputted simulation temperature at each of those 3 points, which corresponds with the 3 points on the physical test bed. The temperatures between the simulation and experimental are then compared and evaluated by the model updater. And the model updater's goal is to tune its model's parameters, in this case being the valve opening percentage and the fan speed. And once it's able to reduce the error enough, it will be deemed calibrated. But how do we actually iterate through permutations of valve speed and valve opening and fan speed? The way I decided to do this is with particle swarm optimization, without getting into the weeds of how every single little aspect of it works. All it does is that it seeks to find the minimum of a given search area. So particles will be initialized onto this plane and will work together to find the global minimum. In this case, the global minimum would be the error between the simulation data and the experimental data. And the particles on the search space, their positions, when I talk about positions, I mean their positions equal the valve speed and the valve opening and fan speed. So how do these particles move throughout the search space? So again, particles are randomly initialized in the search space. Those particles' positions are then evaluated. Depending on how good it was, the global and personal best positions will be updated. And to get its new position, a new velocity component will be calculated and added to the particle's new position. So you can see the equation on the bottom. Velocity is composed of three components. You have the one in blue, inertia, the one in yellow, that would be personal, and the one in green would be social. So now we know how the particles move throughout the search space. How does this algorithm interact with and handle real-time data? So the goal of it is to seek and minimize the difference between simulation data and the real experimental data using our cost function, which is just RMSE or standard deviation. The PSO will continuously update on a 5-minute window of data until a new window of data becomes available. You can see on the figure on the right, on update window 3, that's the current window that's being updated on. So the PSO will go through permutations of valve opening and fan speed until enough data is collected to form a new window. And you can see in update window 4, you do have some data, but not enough data to fully complete a window. So it needs to wait until there's enough. So now since it works by a sliding window, how do we decide the size of the window? The size of the window is largely dependent on how fast one individual simulation can run. So what we did was run 1,000 simulations in order to get timing metrics of it. And you can see that we got the mean, the standard deviation, as well as the max time. And all these are used to determine the size. So let's say, since our average time is 20 seconds, let's say we wanted a fairly small window of about 100 seconds for a time window. We would only be able to evaluate 5 particle positions before a new window is available. That might not be enough time to find the optimal parameters. So that time window might be too small. So we decided to go with a 5-minute window for this investigation. Here is the algorithm flow chart. I'll quickly walk through it. So the start of the algorithm is we initialize all the particles on the search space. Then we wait for a 5-minute window of sensor data to be filled. And then once that window of sensor data is available, the main loop of the algorithm will begin. Main loop starts off by configuring the model's heat plate temperature, and then it goes into the particle swarm loop, where we use the particle's position to set the model's valve and opening speed, and then we evaluate that model using the cost function. The algorithm then checks to see if a new window of data is available. If there's not one available, we'll update that particle's position and switch to the next particle. And we'll continue evaluating particles until a new window is available. Once that new window is available, a random number between -1 and 1 will be added to each particle position. This is very important because as your system changes over time, the optimal parameters to calibrate your virtual representation to your physical twin will change. And this means your global minimum of your search space will change. So to keep your particles from getting stuck at the global minimum of a previous window, you need to have this degree of randomness in it. And after that, you reset the particles cost and global cost, because the cost of a previous window should not affect the cost of the next window. And this process continually repeats, going through windows of data. And at the end of each window, a calibrated model is returned to the user. Here are the results from this first investigation into the cooling loop, small cooling loop. So you can see the results on the left where I to initially I wanted to start the model updating scheme from a bad initial position. So if you look at the bottom left of the first graph, you can see the simulation temperature is way off from the real temperature. It takes about 2 windows before it's able to finally gather itself and starts to fit itself back to experimental data. But you can notice that throughout the experiment, I make physical changes to the system, such as turning the radiator on and off and turning the valve closed and open, as well as turning off the heating plate. You can see how this has an effect on the accuracy or the error of the system when looking at the figure to the right. Anytime a physical change occurs, error quickly jumps up, but then it's quickly reduced after 1 or 2 windows. So that's the end of the first investigation. The second investigation, it would be on a system called the de-risking station. After finishing my first paper, the IDTC one, which is the first investigation we went over, I had a couple goals I wanted to do in order to improve the accuracy of it. So the first one is work on a much more complicated electrothermal system. And the second thing I want to do is improve the data processing of the ability of edge computer to increase the complexity of the PSO algorithm. And I also wanted to prove how the cost function hyperparameters of the particle swarm algorithm in order to increase accuracy and performance. So getting into it, the de-risking station is a little bit more complicated than the previous system I talked about. It's comprised of 6 major components. So you have the power modules, the radiator, power supply, the pump, a heater, and a tank. On the diagram on the left, it shows how water circulates through the system. So for initially, distilled water is pumped throughout the system via a submersible pump. This water then enters a water heater where it is coupled with a power supply to simulate the waste heat or dissipated heat of various power electronics. This heated water then goes through the power modules. For the test that I did, the power modules were not operational. So normally you would expect the water to be hotter after going into the power modules, but in this case, since they were not operational, they just act as heat sinks. So after going through the power modules, they go through the radiator where the water is chilled and they go back into the tank. There are thermocouples instrumented throughout the entire de-risking station, but there's really only 4 points I wanted to focus on. And those 4 points are 1 thermocouple inside the tank, 1 directly after the water heater, 1 on top of the power modules, and 1 directly after the radiator. Here's my virtual representation or SimScape model of the system. Again, I wanted to tie the system to its physical twin, grounding in some sort of reality. And the way, what input I use is the same simulate dissipated heat that I inputted into the physical system. That value I put into this virtual model. That model is then ran, and the simulated temperature data at each of the 4 points is compared to its real experimental data. And the model updater, in order to reduce this error, updates various model parameters within the SimScape blocks with the green stars on it. One of the goals was to improve how the cost function works and how the hyperparameters work. So in this, I created a system that would help. So depending on the error between the initial temperatures, the algorithm will update its hyperparameters. So when looking at the graph to the right, you can see that there's a large error between the initial temperature of the simulation and experimental. This will start a recovery step. This recovery step will change the cost function and increase the particle's acceleration to induce a much more rapid exploration of the surge space. Calibrated is kind of the opposite of recovery, where it lowers the particle's acceleration just so it can more finely tune the model parameters. Install is a mix between both recovery and calibrated. Here is the timing distribution for this model. Again, we ran it for about 1,000 and the mean time is 4.63 seconds with a standard deviation of 0.634 seconds and a max time of 16.925 seconds. Here's a demonstration of how this algorithm works. Again, once the algorithm starts, it initializes all the particles, then it waits for a 10-minute window to become available. Once this window is available, the particles will iterate over permutations of model parameters in order to calibrate the digital twin to its physical twin. Then once a new window is available, it'll begin working on that window. And this process continues on indefinitely. To gather data to verify whether this model was accurate, we create a 10-hour load profile of a simulated ship. It was constructed in MATLAB and deployed onto a power supply with the water heater in order to replicate the ship's power electronics dissipated heat. And this resultant temperature from this experiment was captured by the thermocouples at each of the 4 points. Here are the results from that experiment. This 10-hour load profile is repeated 4 times. And on the graph, you can see the temperature directly after the water heater, as well as the power dumped into it by the power supply. Here are the raw test results from this experiment. You can see the temperature follows what you would expect at each of the 4 points, that being after the heater, the power module, after the radiator, and the tank. This data was then used to help manually tune the model to this data. The manually tuned model is relatively accurate when looking at the performance metrics. And later in the future slides, I used this to create various scenarios, but create various synthetic scenarios. To test the robustness of my model updating scheme, I want to compare it against the manually tuned model that I just made and showed. So when looking at the graph in the top right, the manually tuned model without model updating was run for the first 3.5 hours. And at that 3.5 hour mark, I randomized all the model parameters to see if the model updating scheme can react and recover from a bad initial state. And when looking at the error graph on the very bottom, you can see the initial jump in error when models are parameterized to how it decreases the error over the course of 2 windows and is able to recover. And even past the 2 windows after that, the model accuracy increases even further than its manually tuned model. That's best shown by the performance metrics in the bottom left, where the manually tuned the model updating scheme is able to improve the accuracy of the model upwards to 90%. To Again, using the manually tuned model, I use it to create synthetic experimental data. This way, I didn't have to physically run a 10-hour test myself. This is to determine whether the model updating scheme can handle physical changes in the physical system. So looking at this scenario is power modules dissipate heat. So at the 3.5 hour mark, power modules were turned on, supplying 600 watts of dissipated heat to the system till the very end of the test. You can see the model updating scheme initially struggles to fit the simulation to its experimental data, but after 2 or 3 windows, it's able to find the optimal model parameters. For the second scenario, similar to the previous scenario, the discontinuity happens at the 3.5 hour mark, in which insulation falls or is removed from the tank. This causes the temperature to jump a little. But when looking at the error at each of the 4 points, since the insulation fell off the tank, one would expect that the largest error would be at the tank. However, this is not the case. This is due to how our cost function functions. So when looking at our cost function, which is the error equation right there, it's the RMSE at each of the 4 points. So the model updating scheme after the installation falls off, it's happy and it's able to satisfy 3 of the 4 points, but while leaving the power module one far behind. But however, after a few recovery steps, it's able to reduce this error and it's able to find the optimal parameters. In conclusion, I created a numerical scheme for updating thermal digital twins. I carried out experimental validation demonstrating that the proposed method can update a digital twin within a reasonable time. And I also improved the performance of 2 static models by linking their dynamic physical twins to its virtual model. Here's a list of publications that I've authored and co-authored through undergrad and graduate school. And this is the end of my presentation. I'd like to quickly say thanks to Dr. Khan, Kerry Saito, and most importantly, Dr. Downey for taking me in and guiding me through my research experience and making me a better engineer. I would like to also thank everyone who I've worked with over the course of these last 4 years. I would just like to say thank you for spending a long amount of time helping each other. And with that, I'm at the end. So is there any questions?